Hello friends, welcome to the course Multivariate Procedure with R. So from this lecture we are going to start a new topic which is linear discriminant analysis, LDA. So the first question comes, what is LDA? What is this linear discriminant analysis? Why it is used? And what are we going to learn in this topic? Suppose I give you a simple question to answer. There is one student who comes before you and you want to know whether this student has a background in mathematics or biology. What are you going to do? The simple solution is that you ask him some questions on mathematics, some questions on biology. And if you see that the person is able to answer more questions on mathematics and the number is significantly larger than the correct answers given in the biology, then possibly you will think that okay, this person has got a background in mathematics. On the other hand, in case if the person is unable to answer the questions in mathematics, but the person or the student is giving more correct answer in the biology subject, then you would possibly consider the student as if the student has got a biology background. If you try to see in all this process, what are you going to do? You have some prior experience that how a student of mathematics or how a student of biology should be. And based on that, you have already collected some observation in your mind, and based on that you have some idea about the probability that the student is going to be from biology background or mathematics background, and based on that you have created a rule inside your mind. So as soon as the student comes before you, you start asking the questions in each of the subject, and based on that you try to fit this data into the rule which is inside your mind, and you try to come up with the final conclusion that okay, it appears that this student is from mathematics background or biology background, right? Similar is the case when we try to see the report of a blood test analysis. Based on that, the doctors always diagnose that the patient has got some disease or not, or a particular type of infection or not. What they try to do? That first they try to take two groups of patients, one group of patient which has no disease and say another group of patient which has got some disease, and then they try to take their blood samples and conduct the analysis based on certain values of the blood parameters. Then they try to see, okay, if this value is below some threshold limit or this value is above some threshold limit, then there is a very high probability that the person has got certain disease or not. Now a new person comes where the doctor does not know that the person has got the disease or not. So the blood test is conducted, and based on the report of the blood test, the doctor looks at the report and tries to classify whether the person has got a disease or not. So this is basically the classification problem. And in this classification problem, if you try to see, there is a rule, and whenever a new observation comes, the values of those observations are substituted in that rule, and we try to see whether the outcome is below or above certain threshold. And based on that, we try to classify the observation into one of the population. Well, this can be extended to more than two populations also without any problem, exactly on the same concepts. So in this chapter, we are going to consider this classification problem. And we would like to see and we would like to understand that whatever we are thinking, whatever we are doing in a very natural way, the way our human mind is working, we would like to translate that rule in a mathematical sense. Why mathematical sense? Because once a rule is in the mathematical way, then people do accept that decision very easily. And then all these concepts, whatever we are thinking, we will try to implement them through some mathematical analysis. For example, you would like to make a decision rule in such a way such that the probability of classification or the correct classification is as high as possible and the probability of misclassification is as minimum as possible. That is what you are trying to do, right? So all these things, how to do them on the basis of a statistical tool is the objective in this chapter, what we are going to achieve. So we will try to take certain aspects. We will try to first create a mathematical framework, a statistical framework, and then we will try to implement them in the R software. Well, I will try my best to keep the level of the mathematics as low as possible. And there are many things which can be done more easily in the software. So I will try my best to give you as much as possible the details, and then I will try to illustrate the remaining aspect through the R software. So with this objective, let us begin our lecture, and in this lecture I am just going to create a background and an overview of this linear discriminant analysis, right? Okay, so let us begin our lecture. So now, first of all, in this lecture we are going to talk about the introduction to classification, which is going to be achieved by the linear discriminant analysis, which is also called as LDA. L is coming from linear, D from discriminant, and A from analysis, right? Okay, so the first question comes here: why classification? So try to consider a situation where we have large data sets and we want to dig out the information from such a data set, and we need to classify and group the data into similar groups, right? Then an investigator makes a number of measurement on an individual, and the investigator wishes to classify the individual observation into one of the several categories on the basis of these observation. Yeah, means obviously we are considering here the finite number of categories, right? So now if you try to see, when an individual comes and the observations are made, then there is a chance that the person may belong to category 1, category 2 or category 3 likewise. So we can consider the individual as a random observation from one of the population. The population is equivalent to different categories. That means this observation is coming from one of the categories, right? For example, in the example of blood test, we have created two populations. One population where the patients have no infection, and other population where patients have got infection. Now a new patient comes, and that is supposed to be coming from one of these population, and then based on the observation, the person or the patient has to be classified as healthy or having some medical issues, right? So the question is now that given an individual with certain measurements, from which population did the observation arise? That means, given the result of the blood test, you want to know whether the patient has to be classified into the patients having infection or patients not having infection. Similarly, looking at the examination scores of mathematics and biology, we would like to classify the student into one of the two population. That one population is of student from biology background, and another population is the population of student from mathematics background. Right. So this classification scheme is a convenient method for organizing a large data set so that the retrieval of information may be made easier. And if you try to understand, this classification scheme actually describes the patterns of similarity and differences among the objects under investigation, right? By the scores in the mathematics and biology subject, you are trying to understand that how similar is the new observation to the students who are having a mathematical background or the students who are having a biological background, right? And all the students, they are suppose broadly classified into two categories, and one category has a student who have got a similar type of knowledge in the mathematics, and another category where the similar type of student have got a biology background, right? So let me try to take one more example. Suppose there are two fields. Yeah, fields means mining fields, right, where we get the ores. For example, to dig out the iron ore, there are certain fields to dig out the coal fields. There are coal fields to dig out the coal, etc. So suppose there are two fields from where the iron ores are obtained. And suppose these two fields are, suppose here field number 1 and field number 2, where the ores for extracting the iron are obtained, but the ores have got different chemical properties, right? So based on that, we have taken some samples from F1 and F2, and we have conducted the analysis, the chemical analysis, that what is the chemical composition of the ores coming from the field F1 and what is the chemical compositions of the ore which are coming from field F2, right? And then we have some here results, say results 1 and result 2. Now a new sample arrives, right? Now this sample can belong to the field F1 or field F2, and we want to know that from where this sample is arriving, right, based on some criteria. So this criteria is now that we try to do the chemical analysis and we try to obtain the values of those parameters in the chemical analysis which was done on the samples from field F1 and field F2, right? So we try to observe the chemical properties of the new sample, and then we try to match that whether the chemical properties of the new sample, they are matching with F1 or F2. And in case if they are matching to both in certain parameter, then I would like to see the proportion of matching of the properties of the new sample with respect to F1 and with respect to F2. And then based on that, wherever is the more proportion of matching, we would like to classify this observation into one of that field, and we will assume that this new sample is coming from that given field, right? So that is the same process which we have done in the case of students and the blood test also, right? Means in the blood test also you had two patients which are healthy and which are not healthy, and then you have conducted the blood test on these two groups, healthy and non-healthy. Then you have got here some data that how the blood test report of healthy person will look like, and how the blood test report of non-healthy person will look like. Now a new patient comes and you try to conduct the blood test. Now based on the properties of the blood test or the values of different parameters in the blood test of the new patient, you would try to see whether this person has more matching with the values in the blood sample of a healthy person or a blood sample of a non-healthy person. And then you try to classify the new patient into one of the group, healthy or not healthy, right? So now in all such cases, if you try to see, the decision is good if the sample is classified to the correct field or correct population. If it is classified to the wrong field, for example, an ore is coming from field F1 and it is classified to F1, then it is a correct decision. In case if the ore is coming from field F2 and it is classified to field F2, then it is a correct decision. But in case if the ore is coming from F1 and classified into F2, or vice versa, that the ore is coming from field F2 and classified into field F1, then it is a wrong decision, and we call it as misclassified. Similarly, if a person is healthy and the person is classified to the group of healthy patients, it is correct. And similarly, unhealthy person is classified to the patient of unhealthy patients, then it is correct. But if a healthy patient is classified to unhealthy population, or unhealthy patient is classified to a healthy population of the patient, then it is misclassification. Similarly, if a biology student is classified into mathematics, or mathematics student is classified into biology, this is misclassification. Whereas if the biology student is categorized into the biology student population, and if a mathematics student is classified into the mathematics student population, then it is a correct decision. So now, how to identify and how to characterize these fields or this different type of population? So each of this field or each of this category can be described by a probability distribution. That is the most simple thing to do for a statistician, that try to characterize the properties through a probability distribution. Right. Now, from this probability distribution, we can calculate the probabilities of classification and misclassification. So, a good classification scheme is one which provides a smaller probability of misclassification. Right. So now, if you try to now consider this problem of classification in a different way, then the problem of classification can also be considered as in the framework of a testing of hypothesis. Right. I mean, each of the hypothesis is about the probability distribution of the observation given from a category. For example, say here H naught is that some observation X belong to the PDF 1, and H1 is here, X belongs to here, PDF 2, right? So, and then if H naught is accepted, that means the observation is belonging to population P1, and if H1 is accepted, then the population the observation is belonging to the population P2, right? So this is also achieved in the topic of classification analysis. Yeah, you can look into the actually books. I may not be covering it here, but definitely these things are available in all the standard textbooks. So our objective is now to find out a classification rule to accept the correct hypothesis and reject the other hypothesis, in the case when we are trying to view the classification problem from the testing of hypothesis framework point of view. Right. Now, when we are trying to think about the classification approaches, then we have two types of analysis. One is called discriminant analysis, and another is cluster analysis. Yes, after this LDA, we are going to study the topic of cluster analysis, right? So, what is the difference between the two? In both the cases, we are trying to classify an observation. In clustered analysis also, you will try to see that we have a similar objective, but the main difference is that in discriminant analysis, we are going to develop a technique for grouping individual observations or the objects into some known group. That means this population is known to us a priori. For example, we knew that we have two populations, one of student coming from biology and say another student coming from mathematics. Similarly, we knew that we have two populations, one population of patients who are healthy and those patients who are not healthy, right, with respect to certain disease. And similarly, the OR fields, field number 1 and field number 2, they were known to us, and we knew that this observation is going to belong to one of these categories. So, these groups are known a priori, in which the observation has to be classified in the case of discriminant analysis. And you will see that when we try to do the statistical analysis, then we are going to consider or find the linear discriminant function for classification, right? There can be a non-linear discriminant function also, but anyway, we are going to consider here only the linear discriminant function. So that is why it is called as linear discriminant analysis, or say popularly it is known as LDA, right? On the other hand, when we consider the cluster analysis, then the cluster analysis is a technique for grouping the individual or objects into some unknown groups. I mean, there is a huge population, and when an individual comes, then we don't know that what are the different population which are existing inside the large data sets. So the objective will be that first we have to create the population of the similar objects and then classify the observation into one of those clusters. So a data set that contains only data point is available and is without the class labels, that we don't know whether this observation is going to belong to mathematics or biology. There can be more students also with different background, right? For example, if we have a big population of students where we have students from the background of mathematics, biology, commerce, humanities, etc., then we don't know, and we have no idea that whether there are these four categories of student or only three categories of student. That is also even we don't know. So under those situations, we try to go for cluster analysis. But anyway, we will try to take up this topic in more detail later on. Right. So, for example, in the case of classification approaches, let me try to take some more example. For example, these are some very popular things which are happening in a day-to-day basis. For example, we always try to classify the data on economic status in group. For example, lower income group, middle income group, upper income group, or say lower class, middle class, upper class. So these are some known groups, and we try to assign an individual into one of these groups. So this is called as discriminant analysis. Whereas the diseases which look similar can have different causes, and conversely, different diseases from the same cause can also be there, and we don't know. So to understand the treatment, we try to classify the symptoms to diagnose the disease, and these are our unknown groups. That what are the different groups due to which a particular disease can occur, we don't know. So this is under the view of clustered analysis. Right. So the problem of classification arises when an investigator makes a number of measurements on an individual and wishes to classify the individual into one of the several categories on the basis of these measurements, right? So everything is based on the measurement which the investigator is going to make, right? First, the population with known people, and then classifying an unknown person into one of those two population, right? And the problem is this, that the investigator cannot identify the individual with the category directly, but the person has to use certain measurements to make a decision that whether person belongs to the category 1, category 2, or like that, right? So we are assuming here that we are going to deal only with the finite number of categories, or there are only finite number of population from which the individual may have come. The only thing is this, we don't know from which population the observation is coming. And we are assuming that each population is characterized by a probability distribution of these measurements. And we will consider an individual as a random observation from any of these population. And now the question which we want to answer is that, given an individual with certain measurements, from which population did the person arise? Right? Or given an individual, from which population can this observation be classified? Right. In some instances, the categories are specified beforehand, in the sense that the probability distribution of the measurements are assumed to be completely known, right? And in some cases where we do not have this complete information, the form of each distribution may be known, for example, but the parameters of the distribution are not known, and so in such cases they must be estimated from a sample which is arising from that population. Right. For example, if I assume that the population is normal mu sigma square, and suppose if the value of sigma square is known, suppose, and we don't know the value of mu, then we have to take a sample, and then we have to estimate mu. Now you know that sample mean is an unbiased estimator of population mean. So then x bar sample mean can be used in the place of population mean, and the same thing can happen to the case if mu and sigma square both are unknown. Both can be estimated on the basis of given sample of data, and they can be replaced back to those places where we want to use these values. Right. For example, in case if I try to illustrate that how are you going to do it, suppose there are some prospective students who want to apply for admission in a college, and this has to be based on certain examination. So they are given a battery of tests. Battery of tests, you who can say that certain question, for example, whenever we go to appear in any entrance examination, we are given say this 100 objective question or 10 question like that, and we have to answer them. Based on that, we are going to be classified as selected or not selected. Right. And then there can be various aspects on which these batteries can be given. For example, so finally what will happen that we will get here the vector of scores, which are the set of measurements, say for example x. And now those prospective students, they may be a member of one population consisting of those students who will successfully complete college training or have potentialities for successful completing the training program, or the student may be a member of other population, those who will not complete the college course successfully. So that is really happening in practice. That why do we try to conduct the entrance examination in a college? We always want to test whether the student can complete the degree from that college or not. And based on the level of education, they try to classify different sets of students as classified, or say as classified into who are selected, and classify them as who are not selected. Right. So the problem is to classify a student applying for admission on the basis of his scores on the entrance examination. Right. You always say the cutoff is say this 90%. That means any student who is getting more than 90% of marks is eligible to take the admission in the college. Or if the cutoff is say lower than 90, that means all those students who have got less than 90% marks, they will not be given the admission in the college. Right. So in other cases, the form of each distribution may be known, but the parameters of the distribution must be estimated from a sample from that population. Right. So in many cases, you know that we don't know that what should be the cutoff, but we simply try to say, okay, means top, say this 20% quantiles student can be accommodated. So we always try to find out the quantile of the distribution, and we say that okay, means all the students who have got the marks more than the 80th quantile, they will be admitted, and all those students who have got the marks less than the 80th quantile, they will not be admitted. Now this 80th quantile can be any number depending on that how many marks all the students have got during the examination or in the examination. Right. So now in constructing a procedure for the classification, it is desired to minimize the probability of misclassification, or more specifically I can say it is desired to minimize the average on the average the bad effects of misclassification, right? And we want to maximize the probability of classification. And also obviously the total probability can be divided into a two-part: probability of classification and probability of misclassification. So if probability of misclassification is minimized, obviously the probability of classification will be maximized, right? And so on. So some important assumptions in the discriminant analysis, what we are going to understand here are the cases must belong to one and only one group. Or in other words, the group must be mutually exclusive, right? You cannot say that an individual observation is belonging to population 1 as well as population 2. The number of cases for each group must not be greatly different, right? Means you cannot say that one population has only 5 observations and say another population has 500 observation. Yeah, the number of cases in all the populations should nearly be the same, or there should be not say high differences, right? And the cases must be independent. Discriminant function performs better as sample size increases. If you try to increase the sample size, you will get a better reply or more dependable reply. But that is a statistical process, that if you try to increase the sample size, we expect that in a good statistical process the decision will become better. So a good guideline is that there should be at least 4 times as many as sample as there are independent variables, right? Because it is like that, suppose if you say that you have got 5 variables on which you are trying to take the observation, and then you have only suppose 6 observations, that will not actually work. Well, that's an empirical rule, what I have told you, that okay, if you have more number of variables, then obviously you should have more number of observations also, otherwise the estimation of parameter becomes a challenge. You can estimate them, but the quality of the estimates may not be good. Right, and this discriminant analysis, what we are going to consider is highly sensitive to the outliers. That if you have a very high extreme value in the data set, then this linear discriminant function will deviate, right, a lot. So, and each group should have the same variance for any independent variable. That we don't expect that the variances of different population are varying a lot. Right, you can have different populations with different variability, but then there will be a loss in efficiency. And but if you are getting the samples from different population which have got the same variability, then the results will be good. And so the first option is this: if you are getting different variances, try to use some transformation to make them equal. Otherwise, we have the procedures which can be used when we have different variances, right? So the independent variable should be multivariate normal. This is a good assumption, but I will try to show you that we have procedures here which do not depend on the multivariate normal distribution also. But if you want to extend this discriminant analysis to a test of hypothesis other aspect, then you will need this multivariate normal distribution. So it is a better option that if you can assure that the normality is achieved in the observations. But if not, then there is absolutely no issue. We have base procedure rule which does not depend on the form of the distribution also. Right, but the good part is this: the form of the linear discriminant function will come out to be the same whether the normality is assumed or not. Right, and I can say it was similar to the ordinary least square estimator in the case of linear regression modeling, where the ordinary least square estimator and maximum likelihood estimator had the same form, beta hat is equal to x transpose x whole inverse x transpose y. But later on you said that okay, if you want to go for confidence interval estimation and test of hypothesis, then you need to assume a probability distribution. So in the case of least square estimation, although in the beginning we have not assumed any probability distribution with the random errors, but later stage we assume them to be normally distributed. So similar is the story here also, right. So now with this we come to an end to this lecture, and you can see here that this was basically a storytelling type of lecture, but it was important in my opinion, because when we are trying to start a new topic, it is very important for us to have an overview, so that from the next lecture, when we are trying to do anything from the statistical or mathematical framework, then we know why are we doing it. Now, if I try to show you that how are you going to calculate the probability of classification, then at least you know that why you are doing it. You are doing it because you want to minimize the probability of misclassification. And then you would, and then whatever analysis I am going to do, you will understand that why I am doing it, because I want to make here a rule. I want to formulate here a mathematical formula based on which we can do the classification. And what are we going to achieve? That is also known to you. That first we will have population with some known features. We will try to create a rule, and then we will try to make a decision rule that if an unknown observation comes, then how it is going to be classified into one of these population. So that is why this lecture was important. But definitely we are going to use different concepts like matrix theory, multivariate normal distribution, etc., their estimator. So it is good if you have a quick review of those lectures which we have done in the past. So you come prepared with these things, and I will see you in the next lecture, and I will continue with the linear discriminant analysis. Till then, goodbye.